Nice.
Just one sec while it gets going. Cool. Yeah, so there's a few things to go over in terms of like SimPEG pull requests, a few updates. We can fill you guys in on Doug and Soggy and how that's going there. But maybe we'll do that afterwards. Yeah, so we'll let Thibaut get started.
Okay. Hi everybody. So not that much code for me today. Like I'm working on it, but I still have some numerical issue to figure out. So today I will mostly focus on showing you like the approach I choose so far for a project I gave me. So basically, I try to like unfollow the assumption we're making about the objective function, and like the main objective with that was basically to design a framework where I can work to put prior information for my model, like petrophysical information or structure, but trying basically to get rid of the usual bound constraint we put usually in the GIF tool. The thing I didn't like about it was that it's usually it's local constraint, and what I'm trying to do here is like to design global constraint on my whole model. And so my motivation for that too is that in my own project, in my area, I'm sorry I cannot show you any data from that today, but is that I have tons of information at the mining camp scale, but at the scale of my of the area I'm working on, I don't have that many information. So I'm trying to find ways to use this global information and bring it to my small area. So like here I have like so that's here I just have a very schematic drawing of the problem I have to in my area is that I have a slightly conductive and very chargeable target, but under and chargeable overburden too. So like when I do the normal inversion I have, it's seeing nothing, like as we can see in the middle slice here. So that's my model, and that's what I retrieve from inversion, and that's basically what I see with my real data too.
And this is your DC data?
I'm using DC data for this one, for this story, for this example.
And it's a gradient array.
And I choose a gradient array because I'm putting it much more difficult to detect things at depth, because that's kind of I have some gradient array in my data, in my real data too. And the main goal at the end will be also to say that if we constrain, for example, the petrophysics or the structure, then we don't have to put an artificial distance or depth weighting in our physics. So because that's what I retrieve, so I don't see anything, but we see that, for example, at the surface here, like my log conductivity is my conductivity can be much higher than what I have in my model, and if here I have let's say a detectability of my sphere in the data. So here I have the overburden conductivity, here I have the sphere conductivity, and I'm somewhere around here for my model. So it's like I have a change of at least 10 to 15% of the data due to the sphere. So I detect it. The thing is that can I retrieve after that in the inversion? And so that's kind of like the motivation at the beginning of what I'm going to show you today. So let's get moving. So I try to unfold it from a probability point of view. Like there is nothing too crazy, but for me it was really like a high opener on all the assumption we're making with the objective function. So the first thing is that we have our data D, and we're gonna basically consider it as a realization of a multivariate probability distribution. So this observed data is like So it's a realization of a probability distribution P of D, knowing that I got my physics, my model, and some covariance on my data. So basically, in our case, that would be my noise, and it can be correlated or uncorrelated. And if it's uncorrelated, it's just going to be a diagonal matrix.
And you're assuming that that's known.
We're assuming that that's known, but we're going to see that we can, there are many ways we can adapt it to our problem too. So maximum likelihood is first approach, like that's the naive one, will be the maximum likelihood estimation. So this data is what I know, and basically, so I have a realization of like a multivariate Gaussian that we can see here, like for just 2 variables, and basically knowing the data and assuming I know my probability distribution and I know my physics and my covariance matrix. I want to play on the model M, so I maximize the likelihood, so I maximize the probability of my data. What I'm saying is that I have a data and I'm considering that's the most likely one, and I'm gonna just then play on the model parameter to make the data the most likely. That's kind of the approach of that. Does it make sense for you?
I think so.
Yeah. It's like we have a realization, and assuming we know the distribution, it's like, okay, what's the model that gives me the highest probability to get this data?
Okay. Yep.
That's another way to put it. So the bar here just means that knowing A, knowing M, and knowing sigma. So I'm just going to do that through like an uncorrelated Gaussian example. So I'm going to assume that my probability P is just a multivariate Gaussian. So it's a Gaussian in all directions. Like, and so for each parameter for each of my data. So
it's a Gaussian. The y-axis of that is the data. Is that
like if I look at this one in 2D,
yeah,
one axis will be data 1, the other axis will be data 2.
Okay.
And then on the Z here have the probability density.
Okay.
So here, and you see, like I put it shifted here, and it's not, and it's actually a bit skewed too. So my maximum probability will be here. So like around 2 for this guy and around 0 for this one. So if I assume Gaussian, what I need is a mean. So my mean will be if I'm in a linear case, just to make things simple for now, my mean will be my physics times my model, like M as usual. And if I assume an uncorrelated noise, I will just, my covariance matrix will just be a diagonal. So if I write it as a Gaussian, it will be proportional to, I just drops the multiplicative constant here. So that's going to be, this probability going to be proportional to the exponential of -1/2 AM minus D transpose sigma minus 1 AM minus D. So does that start to look familiar at some point? Yes. So as I said before, we want to find the model M that maximize the probability to get this data. So I'm looking for the Argmax of M of this probability. And a way to do that is it's actually equivalent. Is that if I want to maximize the likelihood, it's like minimizing the negative of the log of the likelihood, because negative log will be negative log will be a concave function. So I would just So multiplying, like taking the minus log of the probability, it's I will now look for the minimum, the m that gives the minimum of the negative log.
Okay.
Right? So if I...
Sorry, why are you taking the log as opposed to just the negative of the exponential? Is that like a choice to scale that, or does that fall out of the math?
That follows the math because you have an exponential usually in the probability distribution.
Yeah.
So if I go back to that, my probability it's proportional to this guy.
Yeah.
So I'm taking the log of it. So I'm taking the log of the exponential.
Yeah. So you're choosing to take the log, or that is the definition of the problem?
No, I choose to take the logs because it's convenient in that case.
Fair enough. Okay.
Like if your function is nice and you want just to maximize this guy, why not? But in that case of a Gaussian and for like many distributions, that could be really nice to take the log of the exponential. So if I want to minimize now the negative log likelihood, so I just drop the exponential here, and the minus times minus here got plus. So I'm looking for the minimum of the L2 norm of AM minus D, knowing the covariance matrix here. So we got back basically what we usually use, but we just derive it from a probability point of view, saying that okay, I will assume that basically in our case that our noise is Gaussian, and that gives us the L2 norm, which is quite nice. But then we can use, for example, other distribution if we have different type of noise. So that's great, and find that if I just want to maximize the probability of the data I have this guy. But the problem with that is that it gives us nothing about the model itself. Like any model that minimizes this function are all as good. So that doesn't really answer our question, because what we're really interested in is not maximize it. Like our naive approach of maximizing the data is not good enough for the model. So like the question after that is to say, okay, I'm gonna reformulate that. Given my data D, and knowing the probability distribution of my data, what's the most likely model? Like what's the model that give me a high probability to get this data, but that also have itself a high probability. So what we're looking, instead of looking for the probability of D knowing A, M, and sigma, now we're looking for the probability of our model knowing our physics, our data, and our covariance. Which can be, but that thing is much harder to choose because we don't know anything about the model at first. And so this approach of like maximizing the probability of your parameters, that's what people usually call maximum a posteriori estimation, MAP. Sorry, like we're gonna have like a lot of overlapping terms during this thing. But so what we do to estimate that, we're gonna use Bayes' rule in probability. So the probability of my model knowing all my parameters now, probability of my data again, knowing all the other parameters, so that's my data fitting term. And I will multiply by the probability of M. So this guy is, and I have a normalizing term here that we don't need to care of. It's just like the probability of the data over like the whole space of like all possible other things. So it's just a normalization term that we usually just compute at the end. We compute the probability of things, and at the end we just make sure that the sum of everything is equal to 1. So it's not a term that we care about. And it's not dependent of our model too. So if I want to maximize this, it's equivalent to maximizing just the guy on top. So now I have this probability of M, and this one is open. I may need to make some assumption for this one. Assumption we can make is that my M is now also a realization of a Gaussian distribution of mean MREF and covariance 1 over beta. Does this look familiar again? And with this one, we will do exactly the same thing. We want to maximize this probability, so we're gonna minimize the negative log of the probability. So this productive becomes sum. And again, for this guy, it's an exponential, so it's gonna drop. So I didn't put the intermediate thing, but when I minimize the minus log of my probability of M, I get back my data fitting term we saw before, and my regularization term that I have. So assuming basically, from the probability we got back the Tikhonov regularization. So why I do, or for me, it was actually very nice to develop that. It was basically because it's make very clear all the assumption you're making on everything with this formulation. You assume that your noise, even if it's correlated, it's gonna be Gaussian. You assume your model itself is Gaussian.
Well, drawn from a Gaussian distribution.
Yeah.
Okay.
Yeah, it's drawn from a Gaussian distribution. And we have made actually a tons of assumptions to get to here. So L2 and Gaussian are very interwave. It's the same thing, just from 2 different points of view. And one thing was nice to look at too is that when we do beta cooling in our inversion, that's what we do actually. That at first, when beta is high, we assume that our model is drawn from this distribution, so in a very narrow space. And the more you cool beta, the more you allow your model to take far away value from your mean. So away from your MREF. Okay, so we got back what we already all known, but as I said, for me, I found it really nice to derive it from this point of view and just putting it under the spot all the assumption behind it. So what can we do with it? First thing you can think of is you just use a different probability distribution. So if you use a Laplace probability distribution, you get back the L1 norm. So that's DOM you use successfully, for example, if you want to recover a sparse model in some basis. That can be in some that can be in the space. But if you want to have your model that is sparse in Fourier or in wavelets, etc., that would work the same. Another distribution that I think is really cool is the student T distribution. It's like a Gaussian, but with easier tails. So it's very nice for outliers, detectors, or if you know that most of your data are good, but you have also a lot of outliers that are hard to detect, and you have enough outliers that it's basically skewed your distribution. I haven't made a distribution for that, but imagine that you have, even if you in an overdetermined case, you have tons of points that follow almost a linear trend, but then you have a lot of very high value on top. In L2 norm, it will just put you in the middle, and if you then outliers are the ones that I don't fit, you're gonna actually throw away all the good data. I can try to do a yes.
We'll see if this. Can you sort of see that?
Yes, sort of.
Okay. We'll take a screenshot afterwards and upload it as well.
So okay, I have like tons of points that is like that have got really high density over this line, but I have also a ton of outliers due to some effect. So definitely just looking at it, like I would like to do like a linear trend like this.
Right.
But if I do an L2 norm, that's what the L2 Leslie square will give me.
Right.
And then I said, oh, all the outliers are outside that window. You get rid of most of your data. But if you do this one, if you say that minus is follow a student distribution, that's what you will retry. So it's very nice for outliers detectors when you have like uncorrelated points that skew your distribution.
Okay. So it's better at looking at correlation, in a sense?
Like this one, like basically it's still looking at the error, but instead of looking at the square error, it's gonna look at the log of the square error.
Oh, okay. Right. So you're basically changing what your y-axis is. You're looking at a different space, essentially.
It's just that you define your errors differently.
Right. Okay.
So for example, if you have like if you basically in L2 norm, if you have like outliers which really push you out because you square the error. So if the error gets really big, it gets even bigger and it's gonna really screw all your distribution. L1, you just look at the absolute value of you just look at the absolute value of the residual, so it's already nicer. This one looks at the log of the square of the residual.
Okay.
So like you see log, like it's something that go like this. So if you here or if you square it and you here, like that's not gonna make that much difference.
Right.
Aren't you increasing some non-linearity in there though, Thibaut, by doing this? Because your derivatives.
That's the problem. Like if you use this type of things, like you can look at what the data fitting terms looks like now. It's not even a norm anymore.
Yeah. So why would you do that? Sounds nasty.
Yeah, that can give you some nasty. Formula. It's still derivable, but it can give you some nasty thing. I've seen some application for seismic, etc. I'm not sure. Like I haven't tried it myself, to be honest. It's just, like as I said, it's just like right now I'm just exploring a framework and see what I can get out of it.
Dom, I imagine in a lot of ways too, you could adopt a strategy like what you've done with the sparse regularization, where you fit it as hard as you can with an L2, so you get somewhere close to a solution, and then you can deal with something that's more nonlinear.
Yeah, no, totally. Or, I mean, I think they kind of want to do this when they are reweighting after a few solves, right? Chris started implementing it with the UBC codes, but yeah, I don't know. It's just another layer on top of it, and it needs to mean something. It needs to give you something out of it, I guess. Work.
Yeah, this one will be, as I said, like if your data, if you have good data, but also some very noisy data, and L2 is not able to sort it properly. Like another tool you can use if you have this type of thing.
Yeah, no, it's good. It gives you a metric, I guess, to reweight your data, right?
Yeah, you reweight your data, and as I said, it's just sensitive to the log of the square residual. So your outliers have much less impact than in L2. Like as I said, I didn't try it. It's really like exploration work for me, like to see, like from this approach, how I can redefine objective functions that fits different problem, to make it very specific to what you're trying to achieve. This one is like, it's one slide for very complex things. I try to look at it. It's like people in machine learning call that a structure sparsity. And it's basic, like the basic idea is that you apply different norm to different part of your model. And you can even compose the different, and you can even put the same parameter in different norms. So then you can deal with dependency between your model. Like for example, if you have your, if you then make M2 0, and if both are non-zero, then regularize them in a L2 norm and stuff like that. So you can actually actually impose structure in our model with that. I haven't seen it done in geophysics yet, but I might explore that. But I try to read it's something very, at some point, very new. Like I read a thesis from like 2015.
Like my thesis.
My thesis, yes, that's kind of what it is. But it's been used for like machine learning application before. So like for here, I just made like a very random figures where like one parameter is drawn from a Gaussian and the other parameter is drawn from a Laplace. So that's something that is to durable. This one is really just like, okay, here is some things that people does, but I haven't dived into it that much. But what I've been working more these days is working on the prior that we talked about. Like so far, we've seen that if you use like a single Gaussian or a single Laplace, we're gonna get L2 or L1 norm. But in my case, for my data, for example, I have tons of petrophysical data, and my goal will be to make it falls into like that my inversion retrieve model parameters that falls into these bins that are defined by my petrophysical data. So that for me, the approach I choose right now is to define my prior as a sum of probability distribution. Or Laplace or whatever you like, but Gaussian is good enough. I can derive it as many times as I want, and it can, if I put n-house Gaussian, I can fit basically any type of distribution. So that's quite nice. So for example, like if I have like that's some sort of thing you can do, like that's from the model I show you at the beginning. And I just use here 5 Gaussian, and you see that I can fit the heavy tail I got here and the different models.
So in this case, you're ending up with a regularization that is like
several
different. Well, you have several different reference models. Is it just a sum though of?
No, because the sum is inside the log now, which make it more painful. That's where I have like some issue with that. I will show it later what that looks like. So here I showed basically the pros, is that with that I can fit any parameter distribution, and it's easily scalable. That's what like something in 1D, but that's something in 2D that you can fit, and you can go in many dimensions up as long as your data keep up with the dimension. And actually past 4 dimensions, probably hopeless, in a way that, for example, in 1D, it's basically an histogram, if you want to think of it. And in 1D, if you want to have 10 bins, for example, you need 10 you can start with 10 samples. But 2D, you want 10 bins for each of the 2 parameters, you need 100. 3-dimension parameter, like for strict physical property, you will need more than 1,000, and it just scales and scales and scales. So imagine that DC-IP data, I have resistivity and 20 time IP time windows. If I want to do a fitting on all these parameters, to be able to start to do a good job, I will need something to the order of 10 to the power 21 sample. If I had 20 time windows and resistivity. So you will better like do some sort of transformation in call or stretch exponential to bring it back to a 3 to 4 dimensional space in that case.
Yeah.
So that's why like this, as long as that keep up is actually important. It's scalable, but mathematically. And with this formulation, it's actually englobe k-means and Parson window as just a special case, where you k-means, for example, would be put your covariance matrix all the same and that are just proportional to identity. And Parson windows is like you have a 500 data point. I'm gonna fit 500 Gaussian, so it's gonna fit perfectly. There are some tweaks behind that, but like we don't need to see it right now. And so that was an early result, but it's not quite there yet. Like this one, I admit that some of my gradient was wrong or anything, but it was like kind of still beginning to give something nice in a way that you see here that I didn't change the scale, but I just get the same scale for my parameter back, and with the same survey and inputting this non-local information into my inversion. And before, the sphere was invisible and it was putting me very conductive stuff on top. Now I got some high at the surface, but I start to distinguish that. So that's kind of the idea. This was an early result, and now my code is all broken, but that was encouraging at that point, and I'm still working on that. And so like now to show what my function objective looks like, that's what it looks like. And that's when it's become nasty. So my data fitting term is still the same, but now instead of a norm, I have the negative log of a sum of weighting exponential. This is nasty. Like the log sum exponential, it's a well-known thing in computer science to underflow or overflow very easily. Hopefully there are some tricks that I still need to implement. The probability here, it's always positive, but it can get as close to 0 like as we want. So that means that I take the log of something that is always positive, but can get close to 0 very fast too. So that cause me also some numerical issue, because I have the log of something very close to 0. So sometimes it can blow up, and that's why even if it's infinitely derivable, the gradient and Hessian can get very big very fast. That's one of the problem I have to face also right now. And the last point, I don't know if it's a problem or not. It just is that in most cases, like this thing, like the probability density gonna be less than 1, so my negative log gonna be positive. But this thing here is like we talk about probability, but it's we should not be talking about probability. We should be talking about probability density distribution. And if probability stay between 0 and 1, probability density does not. So this term can sometimes be more than 1. So I get something in my objective function that is negative as a second term, which should not be a problem. If you really don't want that, you can just shift by a constant to make sure that everything stays positive. It's just like an annoying detail to look at when you look at your log result, and like you see that your phi m is negative. and this one I haven't included in that presentation, but we can like all the same way we include the smallness, etc. We can include the gradient into that thing. And one thing why I mentioned to you that I was really interested into the composable objective function is that for this term, like beta cooling comes very naturally when we have like just a Gaussian drawn from a Gaussian distribution. But this one, I don't have anything with it. Doesn't mean that I don't want to put anything. I will probably put some weight, like define a alpha negative log likelihood or something, like another alpha. But I will definitely use another beta, like a different beta strategy for, like, I don't like what Jaja did in CSM is that he didn't. I don't think he used this framework to derive k-mean. He basically took the objective function and add the objective function you usually use for k-mean, which is like a special case of that one. So it got some simplification. So it's just adding term after your objective function. So we still have a smallness and derivative, etc. And I think maybe it helps. Maybe it helps also like stabilize the problem when this guy become nasty. But definitely, I will that composable objective function will be nice to play with that to be able to play on the different parameter on their own, and so they don't depend on the same beta and stuff like that. For example, this one I don't know if I will. At first, I will not try to do. I will not do a beta cooling. I will do a beta cooling on the smallness, etc. at the beginning. But this guy I will try and make it like stay the same because there is nothing appearing on that side. Like mathematically speaking, in that framework, I don't see any reason to do a cooling. Maybe numerically, but we'll see that later. So that's just an example. So that's my model here, and I just have 5 Gaussian to fit that. That's quite nice. Like, I mean, it's all derivable, etc. In blue, so that's my negative log likelihood of that. But you see, I have some kink here. It's not as L1, it's derivable. It just, as you see, if you look at the first derivative and second derivative, I can compute a value, but it's getting very big, very fast. It's not infinite, it's not non-defined, it's just very big, quickly. So that's what I'm trying to. So that's what I'm working on these days, trying to make this work and going through all the annoying detail, if I want to quote a Rowan website.
Very cool.
Yeah, thanks for the overview.
Yeah, do you guys have questions or things you want to bring up?
No, I'm good. I'm good. How do you foresee you're going to implement it in SimPEG? How do you foresee that it's going to be implemented? Like, you want to write a new objective function, and like it's just a linearized regularization, no?
Right now, how I do that is that I created a new regularization class that I call Petro regularization, and that so it's. And so now in the inversion, in the eval function, like regularization, like it evals the negative log likelihood and the gradient and Hessian of the negative log likelihood.
Okay, nice. Yeah, that's good.
So it's inside the SimPEG framework to give direction, descent direction.
Nice.
Yeah, so actually on that note, I'll switch and show you guys the composable objective function stuff is like pretty close. I would say it's worth jumping in and trying to use it now.
Okay.
So I did create an example. I'm just sharing my screen here. Cool. Oh yeah, thanks. Well, that makes sense.
Cool. And can you make sure that you change the screen on the Google Hangout side of things as well?
Oh yes, good call.
Thanks.
Cool. Can you see that now?
Yeah.
All right. So. So this guy is sitting these ref objective functions. So sorry, there is sort of like two pull requests going on here, but I needed a short example to actually test it out. So I've included the straight ray tomography example. And so this is a bit of a silly example, but it was in an SEG abstract that we did in 2014, where it was using some effective medium theory stuff. So in some ways, like what Thibaut's doing, but in a much less advanced way, but all through mappings. And so in this case, what we did is had like a mixing law that basically comes up with like what the physical properties look like. So based on some distribution of phi, which was concentration, we could come up with a conductivity. And then I wanted to regularize on the total volume, then another data misfit term. So in this case, we did an inversion without it and do an inversion with the volume term. They're both pretty similar, but you get back like closer to the true volume. And if you push it and play with sort of ramping things up and down, you can get actually some pretty cool inversion results. So check out those examples and see if that is working for you. And make some noise when things are breaking, because of course, like it is a first pass, and so there will be weird things that come up, I'm sure.
That's super. I'm very excited to jump into it.
Yeah, and I think it's like it is stable enough. So I've tried both with composable data misfits and composed regularizations, and it seems to be doing reasonable things. So yeah, give it a try. And
Perfect.
if somebody has a cool idea for a paper for using this, I would be very keen to join in on that.
Yeah, for shizzle. Okay, well, I'll implement it.
That's awesome. And then the other pull request I wanted to go over, and maybe I'll let Rowan jump in briefly here too, is pulling out the mesh class. And so now it's in the discretize package. So now there's no meshing inside of SimPEG. This is on dev right now, but I would like to get it down to master soon-ish. So yeah, so all the meshing changes can be done strictly in discretize. And then Rowan updated the Richard stuff.
Yeah, which I mean, there's it works better now. So you can invert for any of the different sort of empirical parameters. I might do that, like, or talk about that at a later time, because I think it has some application to IP, and anytime we want to do sort of any mapping that depends on the model or on the fields. And I'm sure we'll be getting into more of those sorts of things, especially as we get into joint inversions as well.
Yeah, that would be awesome.
So yeah, I could do that, sort of prepare something for the next couple of weeks. Yeah. And then there's that one other thing about the NumPy and SciPy are no longer, or SciPy sparse, are no longer being exported by the SimPEG import star. So that means you'll probably, if you're relying on those, you'll have to add two other imports at the top of various functions.
Yeah, so I think that makes things much more transparent, but yeah, there's probably code around that used to do that.
Yeah. Yeah, I think it's pretty simple. I don't think there will be any breaking changes other than the NumPy SciPy thing. The discretize package is exactly the same, and it sounds like Joe is working on some improvements to speed, especially on the tree mesh side of things. I'm don't have an idea of when that sort of stuff will land, though.
Yeah. But nice that things are being improved. So yeah, so maybe try that out and we'll try and get that in maybe, I don't know, is it reasonable to do this like today, or do you guys want some time to port things over?
Maybe Dom, do you have any thoughts there?
Thoughts on that?
Oh yeah, sorry, my mic was muted. I was saying that the faster the better. I mean, it's up to you guys for maintenance of the bigger framework, but the faster it's on ref, the easier it is for me to work.
Cool. Yeah, I mean, let's do it today. As long as Soggy, I mean, because he had that SimPEG tutorial thing yesterday, I believe. And so now now that that's done, we can maybe update it and make sure everything's still working.
Yeah, don't kill him.
For him. Yeah, exactly.
Well, he's done that, so we're in the clear. And I've tested against all of the apps and stuff like that, and they're all fine. So I think we can safely go ahead and pull it in.
Excellent.
Just for discretize, so how much changes is it for? Because we don't call mesh anymore, but is it backward compatible, or how does that work?
So you can still import mesh from SimPEG, and all that is a pointer to the discretized package, and everything works the same. So if you say from SimPEG import mesh, you get all of the same stuff.
Gotcha.
It's just that mesh is now a pointer to discretize.
Yeah, it's not its own framework. Okay, sounds good. Yeah, I get it.
Yeah, and this sort of allows people to sort of jump in at different levels, because I mean, so for example, Joe is jumping in on the discretized side of things, which is like finite volume with derivatives in mind, and that's like what that package is for. It doesn't have anything to do with inverse theory or inverse frameworks. Just you want to take a derivative with respect to your properties on the mesh.
Yeah, I see. Yeah, that's all good.
The only thing that might break is if you did anything like from simpeg.mesh import tensor mesh. That will break.
Sorry, can you repeat that? If you do from?
If you have anywhere in your code like from simpeg.mesh import tensor mesh,
okay,
that would break.
Yeah. No, that's fine.
Importing mesh is fine.
Yeah, that's fine. If it's somewhere, we'll change it.
Yeah, sounds good.
I was going to.
And Dom, looks like you have a couple pull requests going on as well with Meg Amplitude.
It's the same. Yeah, it's the same old. It's just man, it's bug hunting. One thing though that would be nice to change is the print statement. When we're solving, can we print like at the end of everything after the directives are applied, basically? Well, I should say before the directives are applied. We can go. I'll create an issue.
Yeah, that would be great if you could just create an issue and give some context around that and why it's broken. That would be super helpful. Because I don't have any strong preferences without sort of seeing one way or the other.
Totally. Okay, I'll do that.
Sweet.
Perfect.
And then also with regard to printing, I've been looking at some other table stuff. There's some good stuff out of AstroPi that we could possibly rely on, or ask them to break it out or something like that. I don't know.
For like print to file, you mean?
Yeah, print to file and like console logging, which is similar to what Kutney talked about last week or 2 weeks ago. Okay. Yeah, so there's some maintenance there because our iteration printers are terrible.
Well, they do the trick. It's just
they do the trick, but especially as we're going to this composite objective function stuff, it's sort of difficult to see all of the various pieces all at once.
Oh yeah, this John guy, what's his name? Nyquist?
Yeah.
Jonathan Nyquist?
Hmm?
Yeah. So a little bit of cold shower. Eh? We need better examples.
Yeah. Well, I think we always need better examples. That's never going to change.
Nah, it's positive comment. Positive comment.
Yeah.
Absolutely. Yeah.
Well, and from talking with Doug and Soggy, it sounds like MT is one of the things that is like been quite important both in Indonesia and in India. And so like getting some of those examples built up, I know he's not on the call, but we'll just call him out, that would have a big impact. So that's exciting.
Oh yeah, for sure. Free empty.
Yes, exactly. Cool. So for next week, is there anybody who has something in mind that they would like to talk about, bring up? Yeah, any thoughts on that? Resounding silence. Okay, well, we'll figure that out.
Yeah,
Just shoot a message on
I could potentially do something on that Richards equation, sort of going through that again. That would force me to write some stuff down on my thesis, so it would be helpful. Excellent.
Okay, cool. Thanks, everyone.
Cool. All right.
Thank you.
Thanks, guys.
Have a good day, guys.
Talk to you soon.
Good.